Okay, 3.2 part B. In this one we're going to be going over the same two functions, standard and factored form, but doing a bit more analytical analysis, I guess, with each of these. So first thing, what is vertex form and what is standard form? So vertex is y equals a x minus p squared plus q. Don't forget the squared up there too, a lot of people do that. And standard form is y equals ax squared plus bx plus c. And how are these two things related? You can actually turn one form into another form. And we're going to try that here because there's going to be a definition that we can use from that down here. So let's do that by expanding this form. And you can expand without numbers in there. You can expand with just the letters. And that will show you the way it works every single time, regardless of what numbers you would fill in for A, P, and Q. So expanding this, first we're going to square the brackets. So it's going to be x times x is x squared. X times negative p is negative p, and negative p times x is another negative p. So it's actually negative 2p x. There's kind of a fast way to do this, but if you have to draw it out, you can draw it out. Really, this means we're doing x minus p, x minus p. That's what the squared means, and I'm actually taking both the inside ones, so that's an x negative p and a negative px. That becomes two of them. And then negative p times negative p is positive p squared. Plus q. Expand the a. So ax squared negative 2apx plus ap squared plus q. Okay, so now we're actually pretty much done. We're entirely expanded, and the thing we want to focus on is where our different values of x are. So there's our first value of x. This is our single value of x, and there's no other terms with that. And then everything at the end is actually just our constant. All of those would be numbers once you fill in a, p, and q. So all of those actually would equal c. So we can actually write that. We know c is equal to a, p squared plus q. If you were given a vertex form, you could find what the y-intercept is this way, although there's probably easier ways to do it. So this formula isn't all that useful. But the next one is, everything in here has to be our b value, because that's what fits in our formula for b. So b is equal to negative 2ap, which is really, really useful, actually. Now we want to go down here. For any quadratic function in standard form, the x-coordinate of the vertex is given by, so what is the x-coordinate of the vertex? That's our p, right? So we can actually solve for p here, and we can actually have a formula. So if we solve for p, p should equal, all of this would go down, so it would be negative b over 2a. If you were in physics, that should be pretty easy for you. You'd probably do a lot of things like that in physics, rearranging to solve for p. And this is actually a formula that's really, really important. P is equal to negative b over 2a. That means if you're given this form right here, you can actually find the x-coordinate of the vertex by taking negative b over 2a. That's it. So let's try it in action. For each of the following functions, determine the vertex. We only can find the x value of the vertex at first. So the x value of the vertex, p, is equal to negative b over 2a, or some people call it x, but x is really kind of more generic than that, which is equal to negative 6 all over 2, because a is 1. So p is negative 3. Yeah, that's nice and easy. This actually, if you could do it really fast, this actually could be a good way of going from standard form to vertex form. We have another method that we're going to do in 3.3 called complete the square. But this probably could get you there as well. Again, you probably have to do some other things. Now we have the x value of the vertex, but we want to know the whole vertex. So what we want to do there, since we already know the x value of it, all you actually have to do is sub that into the formula to find what the y value would be at that point. So sub x equals -3. So y is equal to -3. Always sub in with brackets because the whole thing needs to be squared. Plus 6 times -3 plus 5. And if you do all that, you should end up at -4, I think. So that's 9 minus 6, 12, 18, 14, yeah, -4. You could have actually used this other formula too to solve for q, but I usually do it this way. So you know the vertex is -3, -4. Not too hard if you can remember that formula. When we get into the next part, this is actually going to be kind of part of the quadratic formula. So if you memorize this now, it'll make the quadratic formula easier to memorize later. And it'll make more sense when we look at the quadratic formula as well. You should pause the video, try this one on your own first. Okay, the solution is p is equal to -b over 2a, which is equal to 12 over 6. So it's equal to 2. Sub that in, y is equal to 3 times 2 squared minus 12 times 2 plus 5. Put that all into your calculator. That's 4. 12 minus 24 is -12 plus 5 is negative, what was that, 7? I think, yeah. So the vertex is the point 2, -7. Okay, hopefully you can remember how to do these questions. You'll probably see something like that on the test. So basically what we're trying to do is be able to solve for all of our key points using standard form. So the couple things that you already know how to solve for is the immediate information. You could really quickly solve for the direction of opening and how steep the graph's going to be. You could really quickly solve for what the y-intercept is going to be. Those things aren't too bad. Now we can solve for the vertex. So that's a new piece in our arsenal. The vertex is a very important point on a quadratic, so now we can solve for the vertex. So the only thing that's left is our x-intercepts, which we already kind of know how to factor for as well. So that should be all of our key points, which means that you can do almost anything you want using the standard form, which is great. So let's put all that in action now. Graph the following quadratic function. State the direction of opening, state all these other things. So you can graph it with a graphing calculator if you want. It should be up. The vertex is at 1, 1, 2, 3, 4. If you're graphing it, and then it goes, the a value is actually -1. I like to use the step method, so if it's -1, I move 1 to the right, 1 down, 1 to the right, 3 down, 1 to the right, 5 down, 2, 3, 4, 5. And then it's the same thing on the other side. And we could label the vertex at 1, 4. So you at least have one key point on there. You can get that with your graphing calculator. You can get that with the table of values. There's a couple different ways you could do that. Table of values, you might be guessing. You could be starting at 0 and you never know where the vertex is going to be. You could use that formula we just did to find where the vertex is so you know how to graph it best. So -b over 2a is -2 over -2 is +1. So you would be able to find that the vertex is at 1 right away. Otherwise, you're kind of guessing. If the vertex is going to be like over at -7 or something like that, you wouldn't want to draw 5 dots around 0. That wouldn't be very good. We need to see how it behaves around the vertex. That's really the key point. Beyond there, it just gets really, really steep, really steep. Those things aren't as interesting. Okay, so what's the direction of opening? It's down. Coordinates of the vertex, 1, 4. What is the maximum value or minimum value? Again, you could solve this doing what we just did in the last question if you had to solve it algebraically. Maximum value is 4. Equation of the axis of symmetry, that is x equals 1. Domain and range. Domain is all real numbers. Range is all real numbers of y, so long as y is less than or equal to positive 4. Should be able to write that pretty quickly. Sorry, this is a little bit fuzzy in my camera, but hopefully we can recognize that. And that's x is a member of real numbers, y is a member of real numbers, such that y is less than or equal to 4. X-intercepts. Well, we've got them here. They look right, but why don't we actually factor this? Because we need the practice anyway. So first we common factor the negative out, x squared minus 2x minus 3. We do that so it's a simple trinomial, because simple trinomials are much easier to factor. Simple means it starts with a positive 1. Our a value is a positive 1. If you have that, then it's very easy to factor, because whatever your two numbers are going to be the roots. Now we look for something that multiplies to negative 2 and adds to negative 3. Well, the only thing that multiplies to 2 is 1 and 2. It has to multiply to a negative number, so one of them has to be negative. Did I do this right? Multiplies to... Oh, sorry. I did this backwards. Has to multiply to the c value, which is negative 3. Has to add to the b value, which is negative 2. Sorry, I got it backwards. That makes sense. So things that multiply to 3 are 1 and 3. One of them has to be negative, so 1 and negative 3 are our values. Yeah, the multiply is always the a times the c value, actually. But if you don't have an a value, then it's just the c value. Because the two final things have to multiply to get there, and that one's always the b value. So minus bracket x plus 1. Whatever these are, just get subbed right in. And x minus 3. So our two roots are x-intercepts are at x equals negative 1 and positive 3. Good. Our y-intercept, well, that takes 2 seconds to find. That's our plus 3. So you want to be able to solve for all of these algebraically or find them algebraically, not just trust the graph, not just trust the graphing calculator. The graphing calculator is a really good way of checking your answers, making sure they make sense common sense wise. Maybe they're really easy to find in the graphing calculator, but still you'd want to be able to calculate them, and you'll have to be able to calculate them when we get to the test. This question's kind of fun. I think you should be able to do it on your own, so I would pause here and try it. Maybe I'll do the first one with you. So A, determine the number of x-intercepts, which is also called the roots, which is also called the solutions, which is also called the zeros. We got a lot of names for these things. These are the 2 times when it touches the x-intercept, the x-axis, sorry. In A, a quadratic function with an axis of symmetry at x equals 0. Let's draw a little graph here. We're going to want to draw a little picture for all these ones and figure out what we're looking at. Axis of symmetry is right along the axes. And a maximum value of 8. So up at 8, there's a maximum, and from there it must go down. So, how many solutions? For A, there are going to be 2 solutions. There's no way you could start up high and go down without crossing that line twice. Okay, try the other ones real quick, if you can figure them out. In B, so you should pause if you haven't. In B, a quadratic function with a vertex at 3, 1. So the vertex is at 3, 1. passing through the point 1, -3. 1, -3 goes through that point. So we know it has at least one x-intercept. Does it have two? Well, yes, it does, because we know that there must be a line of symmetry right through the vertex. Whatever it is on the one side has to be on the other side as well. So there should be two solutions. In C, you very well could, these look like multiple choice questions, right? You might see these in the multiple choice part of the test. A quadratic function with a range of y is greater than or equal to 1. Interesting. Very little information about it, but let's see if it's enough. If y, the range is y is greater than or equal to 1, that means the line of 1 is the minimum value. We don't know where the vertex is. It could be over here, but it has to be the minimum value, so it has to go up. It could be over here, but again, it would have to be aiming up. So the vertex could be anywhere, but no matter what, it will never cross this line. So there's 0 solutions in that one. And D, a quadratic function with a y-intercept of 0 and an axis of symmetry at x equals -1. So lots of information this time. It has a y-intercept of 0. So it goes through the origin, actually. And an axis of symmetry at x equals -1. So right here is our symmetry. Sorry, yes, zoom up. Yeah, so we have the y-intercept on the origin, and we have the axis of symmetry at -1. Now, we don't know where the vertex is, but we know it has to be somewhere on this dotted line. So there's kind of two possibilities. It cannot be on the x line itself. If it was here, it would be a horizontal line, and that's not a quadratic. So it could either be below there or above there. If it was below there, somewhere like there, then we'd have a quadratic that looks like that. If it was above there, then we'd have to have a quadratic that goes down and pretty steep. So no matter what, if it's going to have one intercept here and the vertex on this dotted line, there should be another intercept, and actually we know exactly where it has to be. The other intercept has to be exactly at x equals -2, an equal distance on the other side. This dotted line is always halfway between the two roots. And that's a nice little trick later as well. So this one will have two solutions. Good. Analyzing a quadratic function. So now we get into some larger questions, some analysis of word problems and being able to understand a lot of different questions about them. And usually when you see word problems on a test for quadratics, you end up with 3 random questions. There's all sorts of different key points you could be solving for, like the x-intercept or the vertex or the y-intercept or something like that. And usually you get a collection of different questions. And you need to be able to understand what thing you're looking for and how to find that information. So let's look at this. A frog sitting on a rock jumps into a pond. The height, h in centimeters of the frog above the surface of water as a function of time, t in seconds, since it jumped, can be modeled by the function blah 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 blah. Where appropriate, answer the following questions to the nearest tenth. I actually always kind of skip over this until the very end. I ask, look what it's doing. First, graph it with a graphing calculator. So, we know right away it's going to have a y-intercept of 25, maybe up here. And it's going to be facing downwards. So it's going to be some kind of a graph like this. And that's the frog jumping. I don't think I actually have a picture of it here. I think I don't have a picture of it here. So you'll have to use your graphing calculator and try and find a nice picture of this graph. Maybe fill in roughly what the vertex is, or exactly what the vertex is if you can find it. And state what the window is. So for the window, I would say something like x is between, you put your x min, your x max, y, your min and your max. I can guess what they're probably going to be. Actually, I don't know if I can. The x min definitely is going to be 0, because we don't actually care about what's over here. There's nothing before times 0. The y min is going to be 0, and the y max is going to be something over 25, depending on what the vertex is. So I don't know, this might be 10, this might be 30, this might be 50 or something, and this might be 100. I'm not really sure until you know what the vertex is. So fiddle around with it, fill in that until you get a nice graph that looks like this. So the idea is this is the height, this is time. So over time he jumps, he goes up, he hits his max height, and then he falls down into the water and makes a little splash. So what is the y-intercept? What does it represent? The y-intercept is equal to 25. Do we have units? In seconds, in h in centimeters, 25 centimeters. What does it represent? The frog started 25 centimeters above the water. Because it says the height is centimeters above the surface of the water. So he starts up on some kind of a rock. There's a rock here. What is the maximum height the frog reaches, and when does it reach that height? I'm going to do this algebraically, so I'm going to solve it using our p equals negative b over 2a. You can probably solve it with your graphing calculator, but it's good to be able to do it this way as well. This is going to be my when. This is going to be my x value of it. So sub that in, is equal to negative 150 all over 490 times 2, which is 980. Negative 980, so it's going to be a positive number. 150 over 980 is equal to 0.15. Negative b over 2a, yeah. Positive 0.153, roughly. So not very many seconds. It goes very fast. And then we need to sub that into the equation to solve for the other value. So y is equal to negative 490, 0.153 squared, plus 150 times 0.153, plus 25, which is equal to it takes a little while to enter in the calculator. I get 36.48. Doesn't say how much to round to. To the nearest tenth. So this one is going to be 36.5. And this is going to be 0.2. But I use the full thing in this, or actually more decimals. So the vertex should be 0.2, 36.5. What's the maximum height? You should write this out, but I'm just going to skip it. The maximum height is 36.5 centimeters above the height of the water. When does it reach that? 0.2 seconds into the jump. So we actually have our point here at 0.2. 36.5, roughly. Good. When does the frog hit the surface of the water? So when you get a question like this, you need to look at what is it actually asking for. What key point am I trying to solve for? The surface of the water is right down here, so this is looking for the x-intercept. To find the x-intercept, you need to factor this. Is there another way? You're going to get the quadratic formula eventually. We're not using that yet. Right now it's more about shifting forms. I don't think there's any other way we could solve this. Usually these questions have many different ways of solving them. But so far I think the only way you have of solving this is using the factored form. Or of course using the calculate button on your calculator, and it will find it for you. So let's try and factor this thing. It's going to be a little bit difficult. I'm actually going to do it up here. So negative 490 t squared plus 150 t plus 25. First thing you want to do is see if you can make all these numbers smaller. Can you common factor any number out? And if you can just ignore those things. The common factors actually get ignored just like the negatives in the previous question. So I know they all divide by 5. Do they all divide by 25? 490 does not. Any other number that divides 25? 5 times 5? No. So I'm going to pull out a 5 and then be able to ignore that. And I'm actually going to pull out, well, it doesn't really matter. I'll just leave it like that actually. So if I pull out a 5, 490 divided by 5 is 98. 150 divided by 5 is 30. And 25 divided by 5 is 5. And I don't think those reduce any further. So now we need to find two numbers. This is going to be a little bit of a difficult factor. Two numbers that multiply to a times c. So 98 times 5 is 490. This is negative actually, so it should be negative 490. And they have to add to positive 30. And this is going to be our complex factoring. So this is, we're going to have to do the, I forget what that's called, the decomposition method. So things that multiply to 490. Well, 1 and 490. I might not look for every number. I might jump to a couple in the middle. I know this divides by 5. 490 over 5, which is something we did already. So 5 and 98. And remember, one of them is going to be negative. So we're looking for a difference of 30. So we're still too far apart, so we need a bigger number over here than 5. What about 10? 10 times 49. Well, that makes 39, so we're getting closer, but not quite there. What about 12? Does 490 divide by 12? No. 490 divided by 14. Yep. .490 divides by 14, and now we are, how many numbers? 21 apart? Oh, it might not be whole numbers. That would make things difficult. Just looking if I have the answers here. I don't actually have the answers to this one. 14 and 35, that's a difference of 21. So it's somewhere between 10 and 49. So let me try all the numbers in there, but it might not end up being a whole number. It's not 11, it wasn't 12, and it's not 13. So actually, there is a solution to this, but it's not whole numbers. So we can't actually get this by factoring. So the only way to solve this is going to be using your graphing calculator. So using your graphing calculator, you're going to want to go to get to the graph, and then you want to go to calculate what the x-intercepts are, and then you need to do a left bound, you need to do a right bound, and then you need to estimate where that's going to be. So it's going to be somewhere between, which one's going to be the negative one? This is going to be the negative one, so this is actually what we're looking for. So the time is going to be somewhere between 10 and 14, I believe, if I'm doing that in my head correctly. So try that and write down what answer you get. I'm going to do it on Desmos here, just so I can get my answer. Okay, I get the x-intercept is 0.426. Good. So it was indeed a decimal. When does the frog? So the frog hits the water, so therefore hits the surface after 0.426 seconds. Really short amount of time. He's really not in the air very long. Which makes sense because that was 0.2 seconds in. So it's a bit longer of a fall than it was a rise. What are the domain and range of this situation? So now this one is going to be a little bit different than the other times we've done domain and range because we actually have a real life situation here. So the domain is not all real numbers. The domain is, well, it's going to be real numbers because it's a connected dot, so you can have all the values in there. We can have the 0.2, 0.426. We'd want to round that to just 0.4. It says to the nearest tenth. So it's x is a member of real numbers as long as in the real life what we're talking about is what values of time actually make sense in this question. So you can't have time less than 0. That doesn't make sense in our context. So it actually starts at 0 for us. And it goes until he hits the water. If we want to round it 0.4, I'm going to actually keep more decimals. So it goes till he hits the water. Nothing after he hits the water makes sense in terms of our function either. Range. Y is a real number, so long as y is between. At a minimum, it's 0. We don't care about under the water. And at a maximum, it's 36.5, roughly. How high is the frog after 0.25 seconds? So you can get questions like this. All you need to do, this actually, you always end up with a question like this on the test. All you need to do is, this is your x value, so sub it into the equation. Sub x equals 0.25 into the equation and solve. And if you solve for that, let's see if I can do it with Desmos really fast. 0.25, it should be 31.875. I think that's exactly. So if you round to 31.9, then it's roughly. Good. Write a quadratic function. Let me just talk about that a bit more. Sorry. Just this question right here, finding the x-intercepts. So if it's a decimal, you can't use the factoring method. You can still use your calculator. The only other way you can find this is using the quadratic formula. And we're going to like the quadratic formula quite a bit once we get to it, but that's not even in this unit at all. It's going to be a next unit. And it's going to be a big part of the next unit. It's not the easiest formula. It's a little bit long, but it's one of those ones that you just have to plug everything in correctly, and then you'll solve. So you'll be able to get that eventually, but right now it's just with the calculator. And if I asked you this question on the test, I would probably indicate. It kind of already told you should be using your calculator, so it was kind of a hint that you'd want to do it with your calculator. But it's nice to test it first to see if you can do it on your own. Oh, actually, sorry, last note. First thing you'd probably want to do is look at it on your graphing calculator to see if it looks like a whole number. This one obviously wasn't going to be a whole number. The closest number was 1, and that would have been like way over here. So this one was obviously going to end up being a decimal if you're looking at this on your graphing calculator. In that case, you probably want to skip the factoring and go right to using the graphing calculator to calculate it. That would be the indicator. So always check with common sense first. Okay, let's try this one. A rancher has 100 meters of fencing available to build a rectangular coral. Write a quadratic function in standard form to represent the area of a coral. So this is new. We haven't actually come up with our own quadratics yet. We've only been using ones that were given to us. So this is one way they can come about. These are called maximization problems. So if you have a single restriction, with like an area problem, then you can actually create a maximization problem, which is a quadratic. So what we're going to do is we have 100 meters of fencing. We're going to try and build some kind of rectangular coral. We're going to have a length. We're going to have a width. And we need to make the whole thing equal to 100 meters. Let me make sure I got this question right. So this is a finite amount of perimeter that's given to us. And our perimeter is equal to 2 lengths plus 2 widths. Now what we need to do is come up with an equation for the area. So the area is equal to length times width. And now we need to find a way to combine these two functions together. So what we do know is the perimeter has to equal 100. And we actually have two different equations now. We can sub the first one into the second one to get an expression for just the area and say the length or something like that. So we want to actually solve this for one of the letters and then use the substitution method. So let's actually do that. Equation number 1 becomes, let's solve for L. So 2L is equal to 100 minus 2W. Divide by 2. So L equals 50 minus W. Which makes sense. So whatever length you choose, it has to be 50 minus whatever the width you chose, is what we're saying. So if we chose a width of, say, 10, then the length would have to be 40. Because the two together have to add to 50, which makes sense. Because if these are 50, then these are 50. So whatever the one is 50. The other one is 50 minus that number, is what that says. Now we want to sub that into here. So our new formula is, instead of L, we say it's 50 minus W times W. You do need to get very familiar with these. These maximization problems are very common. Other than gravity problems, which will be a different type entirely for word problems, maximizations do come up probably the second most frequently. So you should become familiar with this. You start with what you know. I actually like to do it this way. Some people kind of do a shorter way. Some people kind of jump right to, they know L is 50 minus W, but I don't like to do it like that. So I actually make it two equations, an equation for the perimeter and an equation for the area. And then I sub them into each other to end up with a single equation. And then we can actually simplify this down. So this is actually factored form. And if we want to expand it out into standard form, see how it's factored means two things multiplying, two values of W multiplying against each other. If I expanded it out, it would be negative W squared plus 50W. And that's our standard form. So we can actually say quite a few things about this already because we already have two forms. What are the coordinates of the vertex? What does the vertex represent in this situation? Well, we don't know that yet, but we can solve it. So let's say P is equal to negative B over 2A. Might be good to graph this out if you want to have a little impression of what we're looking at. But we can solve it algebraically. Negative B is negative 50 over 2A, which is over negative 2. So the answer is 25. The best possible p-value or x value of the vertex, in this case x is width, is going to be 25. You sub that into the equation. Which equation do you sub it into? You could solve for the area here, but we're actually trying to find what the length is now, right? So you could solve that into this one right here. 50 minus 25 is 25, so the length is going to be 25. So width is equal to 25, and length is going to equal 25. You can't really sub it into this one. That's not going to work, but you could sub it into the perimeter formula, is what you want to sub it back into. So the vertex is 25 25. Or actually, that's one way to interpret it if you want to see it, the vertex's length width. Sorry, that doesn't actually make sense if you're trying to graph this thing. If you sub it into this, that actually does make sense. So you sub it into here. Sorry, that was silly. Yeah, these are our formulas that we're working with. There's two of them, which mean the same thing. So you want to actually solve this as our P value, which is actually our W value. You sub that back into here and you find what the A is. So the answer is 25, and then 25 squared is negative 625 plus 50 times 25 is equal to positive 625. That's our vertex. What does it represent in this situation? A maximum area of 625, do we have units, meters squared, when the width is 25. That's what we're looking at. Again, graphing it helps you keep from confusion. So you should graph it, and you should end up with a parabola 25, 50 that opens down and looks something like that, where this is the vertex, and it's at 25, 625. Something like that, and it goes through the origin as well, which is nice. Sketch the graph. Oh, there it is. So sketch the graph you determined in part A. That's this guy right here. You can use your graphing calculator if you want, or we can use some key points. We know we have a lot of things here. So from our first formula, from our factored form, we know the x-intercepts are, in factored form you can just read it, so it's 0. What value of w can you sub in? That should be 50 to make this whole thing 0. You subbed in 50, 50 minus 50 is 0. So x-intercepts of 0 and 50. So that's where we get this and this. We have our vertex already. 25, 625. That's really important. And basically that's all you need to graph it. We could state the y-intercept as well if we wanted to. And that's from our standard form. Have a look. What do you think the y-intercept is? When you look at the c value, which is 0. No c value means a y-intercept of 0. Every time you get a y-intercept of 0, it means the origin is in your thing, which also means that one of the roots is 0. So these two facts go hand in hand. And basically they happen every time you don't have a constant in your standard form. It means when you factor it, one of your factors is going to be just the variable, w or x. So these two things are always related. If the c value is 0, you're always going to have an x or a w common factored, which always means you have an x-intercept of 0. So y-intercept of 0 implies x-intercept of 0. Determine the domain and range of the situation. Domain is x is a real number, so long as x is between 0 and 50. Although it's not really x in our situation, right? It's more w. That would probably be better to say, unless you rewrote the formula with x's and y's. But in this case it would be w, but I'm not going to rewrite that. Range is, it only is for our graph, so it's going to be between 0 and 625. Y is a real number, so long as y is between and including 0 and 625. Good. It's kind of cool, I think, these quadratics for maximization. What you're looking at here is all the different widths you could pick. And this graph is actually of what the area of the overall square would be based on those widths. So if you picked a width of 20, that's going to be not too bad, but it's not the best. If you picked a width of 1, the length would then be 49, and the answer should be 49 then, obviously. So at 1 it should be 49. Same thing if you picked 49. Then the length would be 1, and that also would give an answer of 45. So there's perfect symmetry, depending on which is your width and which is your length. And there is a perfect answer. And in this case, it's the square, which makes sense. I think all you probably could intuitively figure that out. If there's no special restriction, then you're going to want to build a square. That's going to be the best possible area. Identify any assumptions you made while modeling this. What were our assumptions this time? These things there's no perfect answer for. You have to kind of figure it out as you go along. We did assume that all material will be used. We were not modeling any rectangles which did not involve a perimeter of 100. So if there was a good answer that didn't have a perimeter of 100, that we wouldn't have found it. That wasn't going to be the case in this situation, but that's going to be the case in, sometimes in real life that might be the case. So we were assuming that we were going to be using all the material. And also, so in the real world, you might never get that kind of area because you might always have scraps. You might actually have to shrink it a bit more than that. We also assumed all dimensions were possible. All rectangular dimensions. For our graph, we assumed you could make a rectangle that was, say, 27.285 meters across, and then the other one would be whatever the other one is. So it wasn't restricted to just whole numbers, which could be an answer. Sometimes you might get a question where it says the fences come in 1 meter sections, and you have to build a rectangular fence. In which case, it wouldn't be all real numbers for our domain and range. It would actually be all the integers. You could only choose 1, 2, 3, or 4 for the width and the length. There's no such thing as 1.358 or something. And then there's restrictions in the real world. We assumed we could build this kind of, I'm not even going to list that, but that's another one as well. We assumed we could build any rectangle that we could design in the real world. Sorry, really long lesson. I'm already 47, almost 48 minutes in, but let's try and finish this up. Hopefully you guys can get to this the first day, maybe a little bit. Sketch the graph of a quadratic function that has the characteristics described in each part. I like these questions. Label the coordinates of 3 points that you know are on the curve. So x-intercepts of -1 and 3. So -1 and +3. Hopefully these key points are really kind of quick in your head. You're not trying to think, oh, what is an x-intercept? You can kind of just know, well, it's where it touches the x-axis. A range of y is less than or equal to, or sorry, greater than or equal to -4. 1, 2, 3, 4. So kind of down here is going to be the lowest we're ever going to reach, which means our vertex has to be on this dotted line somewhere. And we don't know where left and right our vertex is, but we should be able to find it. It's got to be halfway between these two numbers. Between -1 and 3, so 0 and 2, so it should be at 1. It's got to be there exactly halfway between those two dots. And it's just a sketch. So do it up and label the coordinates of 3 points and label these coordinates. I assume we all know how to do that. B. Maybe try the rest of these if you're feeling confident. Try the rest of these on your own first. You can pause or pause at any point and figure out if you can only do the last two, then pause after this one. One of its x-intercepts at -5. 1, 2, 3, 4, 5. And a vertex at -3, -4. 1, 2, 3, 1, 2, 3, 4. -3, -4. Okay, so those are 2 points. We need to have at least one more point in order to draw our sketch well. So most of these questions are built around the idea of the axis of symmetry. So this guy, the axis, is right where the vertex is. So this intercept was 2 to that side, so the other one has to be exactly 2 to that side. And we draw that sketch. Put your arrows on it every time. Try and make sure it's U'd out, not just a V. Some people start off with not very nice parabolas, and label your 3 points. In C, axis of symmetry of x equals 1. I'll do it with this red line. That's our symmetry. Minimum value of 2, positive 2. 1, 2, so that's our vertex. It's on the axis of symmetry. That's the minimum value, so it goes up and passes through the point -1. 1, 2, 3, 4, 5, 6. So it shouldn't be too hard to put all the key information on that you had in your question, and then you just have to fill in what you're missing. So 1, 2, 1, 2. Because of the symmetry, there should be a point there as well. Arrows, label, good. And the last one, vertex at 2, 5. 1, 2, 1, 2, 3, 4, 5. Y-intercept of 1. Again, we just need to know that we have an axis of symmetry. Every single time, all of our parabolas are perfectly symmetrical. There might be relationships in the real world where one side kind of trails off, but that's not a parabola. That's not how we're looking at them mathematically. We would use a parabola, and we would assume that is perfectly symmetrical on both sides if we were going to use a parabola to model the situation, which might not always be the case. But that one should be like that and label those points. Okay. Finish this homework, and then there's going to be a quiz.